Okay, now we're back from spring break. Last class, I finished chapter 5, but I will go through chapter 5 now just to make a summary of what we discussed. So in chapter 5, we talk about synchronous generator. This is the first chapter after the mathematical description we have in the first part. So basically, we discussed that we need to have a different representation for the grid and the synchronous generator. The grid can respond instantaneously. We're assuming physically that the grid, the energy stored in the grid is tiny. We can neglect that. And for that reason, the variables of the grid can change discretely if that is required for the operation. When the variables can change discretely, when you have a disturbance, a short circuit, so voltages in the grid can change like that. But the state variables that we will have for the generators, they cannot change instantaneously. Why? Because there is an energy involved with that, and the energy cannot have sudden changes. So we started with that. We review the representation of the grid. The representation is going to be this vector of current injected equal to the Y bus multiplied by the vector of bus voltages in the system. And here we consider a few examples, and we review how to build the Y bus matrix. And then we started talking about the generators. So we will have the basic equation for the motion of the generator. But on top of that, we will have controllers. We are not talking about controllers yet, but we will soon. So one of the controllers is the automatic voltage regulator. But also we will have a governor that will control the frequency. And also we will have a power system stabilizer that will help with oscillations in the machine. I presented this. This is the starting point because this is physical. And this is a description of the machine we will consider. We will have windings in the stators. Those are stationary, but we will have winding in the rotor. One winding will produce the flux, and that flux is stationary with the rotor. So if the rotor moves, the flux from that winding will move as well. And that movement in the flux will induce voltage in the stator. But also in the rotor, we will have 3 other windings that are in short circuit, and we call them dampers. Even though we have our first discussion of what the physical description of the machine will be, we focus at that moment on the classical representation. So the classical representation has this structure. We will have an internal induced voltage with a fixed magnitude for that induced voltage. That magnitude can change if we change the flux in the field winding. How we change the flux? By increasing the DC current in the field winding. If we do that, the flux will increase, the induced voltage will increase. But we are assuming all over this chapter that this is fixed. The other part, which is the angle of that induced voltage, is the angle delta, the loading angle, the rotor angle. And that is described dynamically. That will have to do with the motion in the machine. So these are state variables, and that state variable cannot change instantaneously. The other part is that we have a circuit. This circuit is an algebraic representation. This circuit will determine the current that will come out of the generator, and also the electrical power that will come out of the generator. That electrical circuit then will determine algebraic representation, something that can change instantaneously, and that is the current, and that is the electrical power. So what happened in the first example for the disturbance we consider? What happened to the electrical power? So we assume a short circuit at the terminal of the machine, that the electrical power was sent instantaneously to 0. So that is due to this representation. We are assuming that algebraic model. Again, what is the algebraic model mathematically? This circuit, this phasor circuit here that will given state variable will determine a current that will come out of that generator. The rest is the grid. Here we can have anything. We can have multiple lines, loads, transformer, any component, and that is, again, an algebraic representation. For this model, though, we make things simple because that electrical power, we define the loading angle and we improve on the model, and finally we come up with this description. But here, we can ignore this part of the circuit because for these cases that we study, the electrical power that will be generated at the generator can be explicitly determined. We have an expression for that. So we replace that expression here, and basically the model is just these two sets of differential equations. We don't need this because we already obtain an expression for PE. But that was a simplification, and it's not going to be the general case. What happened to my computer? I think that's the end. Oh, sorry. I have another file. Yeah, that one. So we talk about the electrical power. So in that example, the electrical power is actually a mathematical expression we can replace in our differential equation, and that depends on delta. So things were very simple. I said, as we have an expression for the electrical power, we can add an algebraic equation here, defining PE as an electrical algebraic variable, and that would be also a good model. But because this is so simple, we have an expression for the electrical power. We can replace that right there. Why am I talking about this? Because now things will get more complicated. We will not be able to get explicit expression for this electrical power anymore. Yeah. So that's why I am emphasizing on that aspect. With the simplification, then this model is reduced to this. We discussed about the electrical equilibrium point, and we have this description. This is how the electrical power moves. And then we study the operation of the system around the stable equilibrium point under disturbances. And that's how we got different examples. An example B with damping, but the short circuit appear in example C. So we discussed about the short circuit. So there are different disturbances we might have. For example, a single phase short circuit that connect the phase A, for example, and the neutral. But that short circuit is unbalanced, and in this course, we're not going to consider imbalanced situation. So for now, we're just going to consider three-phase short circuit because those are balanced. And we consider that situation there in that example, and we discuss what would happen, and we talk about this. So starting from this equilibrium point, if you have a disturbance, basically, all of the sudden, the electrical power is sent to zero. There is an accelerating power that will push the machine, and the angle delta and the speed will start increasing. Why? Because the accelerating power is positive. At this point, we have the clearing of the fault, and the electrical power change instantaneously to this point. Now the accelerating power is negative. What happened to the speed at this point? Will start decreasing. So the speed was synchronous, increase until this point, and from here, the speed will start decreasing. So the speed decrease, you have a negative accelerating power, so the machine will start like reducing the speed. When the speed is 1 per unit, again, the synchronous one, we will reach the maximum angle. And from this point, the machine will be pushed back to the equilibrium point, and the machine will oscillate around this equilibrium point. So that's what we did. We ran some simulations, and also we considered other cases of the disturbance. this is not a self-clear fault, but it's going to be a fault that is clear by opening the breaker in the second circuit of this transmission line. So that's an example. And in this case, when you have the short circuit, then the grid representation is a little bit different, more complicated, but we went through this example and discussed how we can solve this case. In this case, electrical power is not sent to zero during the short circuit, but the machine will have some power coming out of the machine. So the accelerating power will be less here. An observation based on this, if you let in this example, of course, this is an academic example. If you let this system with a short circuit, the fault can remain there forever, right? The machine will never lose stability. Did you pay attention to that? No, not really. Later in this chapter, we discuss the equal area criterion. So by the equal area criterion, we can see that the increase in the angle will stop when we have an area during the deceleration of the machine that is equal to this part. So by looking at the area, we can see that at some point around here, the machine will reach a maximum angle and come back, and the short circuit can remain there in that example. But another thing we can discuss is, what about if this mechanical power is increased? Well, if the mechanical is increased a little bit beyond that point, then that cannot happen. Yeah, the machine will find at some point some forces that will push them to infinity, and the machine will not be stable. So this stability thing depends on the operating point of the machine, how much power that machine is generating. The larger the generated power, the less the margin for stability. So that's one conclusion from there. And then in this example, we clear the fault by opening the breaker, then the circuit change after clearing the fault, and then we have a new electrical power when the fault is clear. In that situation, we have this case. So we have a negative accelerating power, but when we clear the fault, this negative accelerating power is even larger. So we will stop, the maximum angle will be much smaller than in the previous case. We talk about that and we plot different operating points. And this is the equal area criterion. We discuss what is the meaning of this, and we develop the equation, how this can be implemented. And finally, I left some examples for you to work on. So the first two examples are related to example C. The next following example, 5.3, 5.4, are related to the example D. And the example problem 5.5 is related to this new configuration. In this last problem, we are discussing here what is the benefit from the technical point of view, from the stability point of view. What is the benefit of having a substation here? In the middle of the double circuit transmission line, we'll have a substation. We will have some breakers and transformer, PT and CT, potential transformer, current transformer that can send a signal to the breaker, and we can have that design there. Will that improve the stability? So those are the problems. Yeah. I asked also last Friday if you have questions, we can work on this. But because it was a spring break, maybe you didn't look at this. So I will ask again on Wednesday. Yeah. But go through these problems and see if you can answer it. In the video that you will find in YouTube, then we work on the problem 5.1. Yeah? We were determining the critical clearing angle or critical clearing time using all the analytical derivation from the equal area criteria. Yeah? Any question? No? So try to work on this, and on Wednesday, bring your question if you have any question. And if there is a part here that is kind of confusing or difficult, maybe we can work some of these on the whiteboard. Just let me know. This week also, we will have another homework. So the homework will be related to this chapter 5. So be prepared. I will post that sometime this week, maybe tomorrow. Yeah, okay. So we're moving forward here, and this is going to be chapter 6. We're still not there yet to consider multiple machines in the system, but because we need to discuss a better model for the machine. And this can be very mathematically challenging. So what I'm going to do, I'm going to sketch how this model, more detailed model, are obtained. So it's good. Some part of this probably you will say, well, where did he obtain that equation? But I'm going to just sketch this. And if some of you is interested on this and want to know more details, I can provide material so you can work on that. So we start again from this figure. So we have, that's going to be the physical description of our machine. We will have the stator, in which you have a winding that are stationary, phase C. This is a two-pole machine. So in the rotor, you see, we will have just a flux going in one direction down here. Here is going to be the north, the magnetic pole here, and here the south. So the flux will come out of here, and through the stator will return on that side. But in the stator, we will have 3 windings, one for each phase. And as you can see, the phase C, B, and A are physically rotated 120 degrees. 120 degrees because the machine has just 2 poles. So this is the phase C, but if we change these 120 degrees, you will find here phase B. And if you rotate these 120 degrees again, you will have phase A. So the 3 phases are there, and mechanically, because this is 2 poles, are shifted 120 degrees. The other description is that I said we have a field winding. Here, we will apply DC current, and the DC current will create an electromagnet. We will have the north and south here. By the right-hand rule, the current in the field winding is coming out of here and going there. So by the right-hand rule, the current will point down through this part of the rotor. But also, we will have 3 dampers. We call these 1D, is next to the field winding. But also, we have 2 other windings that are rotated 90 degrees, and we call these the windings in the Q axis. We have 1 and 2 with different characteristics, of course. And finally, one part that we will not be able to go into detail, but we discussed in 325, is how we can connect all these magnetism with an induced force, that because this is a rotational movement, that is going to be a torque. So how we can come up with all this magnetism, we can come up with a torque that will appear, a torque of electrical nature that will appear in that rotor. So we will need to use there the energy and co-energy of the magnetic field. So you should agree with me with this first description. If we have this model for the machine, that's the physical description of the machine. Each one of these circuits, we have 7 circuits, 1 in phase A, 1 in phase B, 1 in phase C, 3 circuits. But then in the rotor, we will have 4 circuits for the field, plus 3 more for each of the dampers, so 7 circuits. You will have in this winding, you will have some flux that will link the winding, the current through those windings. And therefore you will have potentially current going through those windings and induced voltage related to those windings. And here we have the 7 equation. So for the phase A, for example, you will have a voltage at the terminal of the phase A, right here, voltage. But this equation also assumes that the current in the stator go into the machine. So the assumption here initially that this is a motor, synchronous motor. So if this is the voltage at the terminal, somehow we have some voltage source at the terminal. This voltage source will be equal to a voltage drop in the resistance of that winding plus an induced voltage in that winding that correspond to the derivative in time of all the flux that is linking that current. So this is what we discussed in 325, right? So as you can see, it's not very different to what happened in phase B and C. Then you have the same situation for the field winding. You will have a voltage at the field winding. What kind of voltage? DC voltage. We will apply, we will have some circuit, and somehow we will have some voltage DC applied to the field winding. So you will have that voltage. And that will create some current going through that winding. Therefore, this voltage will be equal to the voltage drop because of the resistance plus the induced voltage in that winding. And again, very similar. This is Faraday's law. And the same thing for the 3 dampers, similar equation. And because these are in short circuit, these voltages right here will be 0. So that's the set of equations we are adding to our model. Plus the 2 equations that describe the motion. If somehow we know how much is the electrical torque, that's how the machine will change and move in time. So the other description that we have here is because the stator, the winding in the stator are stationary, they don't move, but the rotor moves, then we need to describe mathematically the angle that we have here. For reference, and we will use this later, we prefer to describe the machine not with this ABC reference frame that we are used for 3-phase circuit, but we would like to express the model using D and Q axis. D will point in the direction of the flux in the rotor, and Q will be perpendicular to that direction. In this case, Q is leading D 90 degrees. So the difference, the angle that you have between the Q axis and the A axis, that is defined as the angle of the shaft, the rotor. So, this is going to be rotating this angle. If this rotate at synchronous speed, this angle will increase linearly in time. As we discussed, the machine can oscillate or can rotate at a different speed. We discussed that in chapter 5. So this angle at some point will not be increasing linearly because we will have some disturbance. That's the model. Do you agree with me until here? Are you okay? Do you understand the meaning of this equation, right? Okay, so here's the sketch. We're not going to be able to derive everything from now and on, but we need to get some understanding of where these models come from. So as I said, we need a simplified representation. Instead of using the ABC signals for voltage and current in the stator, those are sinusoidal signals. So that can be troublesome when we have a model. We want to have something more simple. And for that, getting that simplification, we will use this DQ reference frame. Somehow, instead of having currents and voltage in the phases A, B, C, equivalently, we want to have current and voltage in axis D and Q. So these are going to be equivalent to have sinusoidal voltage and current in phases A, B, and C. We will talk a little bit more about it. This DQ frame is going to be stationary with the rotor. So if the rotor moves, the frame will move as well. So if the rotor rotates at synchronous speed, the frame will rotate at synchronous speed. And now the question, how we get this equivalent representation? How we're going to obtain voltage and current in DQ frame that equivalently will represent the phases? And the answer to that is parts transformation. So there are whole courses related to part transformation. Books talk about not just part transformation, different transformation. And we don't have the time in this semester to go through this. There is a lot of abstract definitions sometimes that can make this troublesome. But here, my intention is to give you a description. Yeah, so we will go through this. So what is a part transformation? Basically, we're trying to transform these sinusoidal signals. That doesn't need to be voltage. It can be voltage, it can be current, it can be flux, it can be any set of three-phase signals. Yeah. So here in the drawing, I put voltage, but it can be anything. So you will have a voltage in phase A, B, same magnitude, but shifted 120 degrees, and C, same magnitude, but shifted another 120 degrees. That's the set of signals that we will have. And by this transformation, what we want to obtain is something that can be described now in D, Q, and zero axis. Zero is a new concept. I don't know if you have heard of this before. Have you heard of zero sequence? Doesn't sound familiar, huh?
Not ringing any bells.
It was,
No.
The zero axis was mentioned in Dr. Thompson's class, but he said to ignore it, we won't be using it.
Yeah. So that can be another whole course on disturbances, on short circuits. When you deal with imbalanced situation, we use another transformation that is the Fortescue matrix. Basically, we decompose these signals A, B, and C into positive sequence, negative sequence, and zero sequence. So zero sequence is a very particular imbalance you might have in the system. So for completeness, in this part transformation, we do have to add the zero sequence. But here is the easy part that we are considering in this class. We're not assuming the imbalance. And because the operation is balanced, the zero sequence will not show up in our description. In a general model, yes, we need to include it. But for this course, this is not going to be different than zero. Always will be zero. So there is no imbalance. Okay. For the rest then, D and Q, these are going to be equivalent signal. This is the voltage BV in the V-axis. So the V-axis is changing with the rotor. So the component of the voltage, transform voltage into that axis is going to be this one. And for the Q, the same. But the main advantage is when this machine is in a steady state, these signals are going to be constant. And that has a lot of value for simplification. Instead of dealing with something that is changing in time, you will deal with something that is constant in a steady state. So that's the main simplification. So the part transformation, mathematically speaking, will be described by this matrix. So you can change not just voltage, any set of three-phase signals. If you have a vector, or in this case voltage at phase A, B, and C, you multiply by the left by the matrix T, the part transformation, and you will convert this into something else. That something else is the D, Q, and zero component of those three voltages. The transformation matrix is this one. The transformation can be done in the following way. We have the axis here. So you have the Q axis and the V axis. The axis for the phase A goes in that direction. So if you have maximum current here, maximum current going through that winding, what happened to the flux in that winding? It will have current going through the winding, and that will create a flux. What was going to be the direction of the flux? Going in which direction? Right-hand rule. If the current is coming out of here, it will go into the A direction. So if the current is maximum, you will have a huge flux going into the A direction.
I thought you were talking about the rotor, not the A base.
No, we're not there yet. So if the current at some point becomes zero, how much is the flux that you have in that wind? Zero. If the current is maximum but negative, well, same flux but pointing in that direction, right? And the same thing will happen in phase B and C. The only difference is that these are shifted 120 degrees in this graphical description. And the other thing, these will depend on time because this angle is changing. So sometimes, the Q axis and D axis will be there, but sometimes will be pointing in a different direction in that place. Let's take this snapshot here. What is the components that we might have in D and Q axis? These are vectors. So if you have a flux going in phase A, how much is it going to be that flux projected over the D axis? When this is angle theta shaft, it's going to be nothing else than the flux multiplied by sine of that angle. And that's going to be the projection over the D axis. And it's exactly what we have there. With some coefficient, I will talk a little bit about that coefficient when we're done with this. How's going to be the projection of this over the flux in phase A over the Q axis? Similar, but the projection now is over the Q axis, so you need to use the flux multiplied by cosine of theta. Exactly what we have right there. What about the B axis? Now you have phase B here, and the axis is pointing in the direction. How much is going to be the projection over the B axis? Well, before was sine of theta, yeah? But now we need to subtract this 120 degrees. So if you get the sine of whatever, you have a flux here, flux going in the B axis, if you get the sine of that, of theta minus 2 pi over 3, then you will get the projection over the V axis, which in this case will point in the opposite direction than D. How much is going to be over Q? Well, the same angle, but cosine. And that will give you this projection here that will fall here along the Q axis. And that is exactly what we have here. What happened for phase C? The same, but phase C is shifted in the other opposite direction. So instead of negative, we have positive. So that's a projection of these vectors in time, is how this matrix of transformation appear. The last equation, as I said, has to do with this zero sequence. And because we're not going to, we need to consider this term when we do the transformation. But in this course, as there is no imbalance, this zero sequence will be zero all the time. This coefficient right here has to do with the property of the transformation. We can play with this. If you make the transfer, this is the original transformation. If you apply the transformation to your signals and you use this coefficient, you will have voltage A, B, and C transform into VV, VQ, V0. The same thing for current. How do you get power in the ABC frame? You just pick voltage VA multiplied by current IA plus voltage B plus multiplied by current B plus voltage C multiplied by current C. That's how you calculate the power, instantaneous power in that system. How you're going to do it in the dq0, friend? Are you going to get it by multiplying BV over IV plus BQ IQ, B0 by I0? No. And because of that, we call this a power variant transformation. This is the original method, but by scaling this coefficient, we can make it happen. And the transformation can be power invariant. What is the meaning of power invariant? That the power in the new variable are going to be determined in the same way that we do it in phases A, B, C. How? BV multiplied by IV plus BQ multiplied by IQ plus B0 multiplied by I0. That would be a power invariant transformation. But that will require another coefficient here. We will not get into that. We are trying to get an understanding of the meaning of it. And this is the original transformation. Are we good so far? What is the purpose of this dq0 transformation?
So that we don't have to use sinusoidal time variance.
Yeah. So the coefficient that we will have here changes in time. Inductance will change in time. And that can make things complicated. But physically, if we can come up with some representation in the axis D and Q, what is the beauty of that? That everything becomes stationary from the rotor point of view. Yeah? So I said if this is balanced, then the component in Q and D are constant. So we get rid of this complication of changing in time. And this is what we discussed in 325 right here. I don't know if you remember that. We talk about the rotating magnetic field. So we will have phases A, B, and C. And here I have the current, sinusoidal current. So, for example, when the current in phase A is maximum, that means that the flux in that axis will be maximum. At that point, the flux produced by the current B and C will be not maximum, but pointing in the opposite direction, right? So if we combine the flux from these three phases, we can get the resulting magnetic field. And this is a snapshot right here at this time. The flux through phase, this is C, is negative. The axis for phase C is this one. So the flux produced by the winding in phase A is C, pointing in that direction. Much larger magnitude than the rest. The other that has a high magnitude is the phase B. The current in phase B is not maximum, but it's large and go in the positive direction. So that's the axis for B. And as you can see, the flux produced by that current will not be maximum, but a little bit larger than the other current. This is the current in phase A, positive, but a little bit. And because it's a little bit, the flux produced in that flux is going to be a little bit in that direction. If you sum all these fluxes, then you have this resulting flux. What happened now, a time step after this? Well, currents will change. The magnitude of this flux will change. And somehow, this resulting flux will change. If we keep moving along time, what we will observe that actually this flux doesn't change in magnitude and will become a rotating magnetic flux. Okay. If we do that now, using B and Q representation, the same flux could be obtained with a flux along axis D and Q. Now, the rotor will change at a given speed, but what happened to the flux in D and Q will remain constant. So that will create a lot of simplification. Instead of having signals that are changing in time to create this rotating magnetic field, we will have constant flux along the V and Q axis. As the rotor is changing, then we will have the same rotating magnetic field. Last time you were with me in 325, I created a code for that. So I'm going to put this in Canvas. So go and play with that code. So I use that code, but now I am adding the V and Q transformation to describe what happened to the rotating magnetic field with this new component. I should have opened this before. There it is. There it is. And we run it. So the first part is the visualization of the rotating magnetic field just using A, B, and C. So the current are moving according to the sinusoidal pattern with A, and I am stopping the code right there. As you can see, current is almost maximum in phase A. That creates a larger flux along that axis. But in B and C, the currents are negative, the flux are negative. That's why B is pointing down here, the same than C, but C is tiny. The sum of these three vectors will give you the resulting flux, which in this case will point in that direction. But if we move this in time a little bit because the signals are changing, we can repeat the same process. And as we can see here, what we observe is that the total resulting flux doesn't change in magnitude, but we obtain a rotating magnetic field. That's again another snapshot of the system at this time. Current, in this case, A and B are positive. A is a little bit, B is a little bit larger. They're positive. And C is negative, almost maximum. That will create a very large flux in that direction, the negative direction of C. The sum of the three of them will give you the resulting flux. So for any other value, then we will continue observing that we have obtained a rotating magnetic field. Okay, so what is going to be the difference now when we use the DQ transformation? How we can obtain this, the resulting magnetic flux in the machine using this DQ transformation. And that's what is coming next. So the situation is because the rotor is changing and the V axes are stationary with respect to the rotor, then the V and Q components do not change in time. And that is the mathematical simplification we achieve with this DQ0 transformation. So this is the first snapshot. And as you can see, for this point, that's the description, but this actually do not lead to any change in the components that we have in D and Q. Of course, the machine will be subject to some imbalance. And the rotors sometimes will not rotate at synchronous speed. So when that happens, the component in the V and Q axis will change. So if you have a short circuit in the machine, these components will have some dynamic response. But we will focus on that component that in a steady state will be a fixed quantity. And whenever you have a disturbance, it will change somehow with some dynamics. So that's the main thing for this description. We want to have something that is simple, something that we can implement and analyze easily. All right. So we were here. Okay, so that's the main advantage of the DQ0 transformation. So now let's go back to the model that we have at the beginning. This is just physical. Voltage at the terminal in the stator, voltage drop due to the resistance in the three windings in phase A, B, and C, plus an internal induced voltage related to the flux link. How we transform this? All of these equations are related, are referred with respect to the rotor. These are stationary with the rotor. These are not. So the transformation is applied to this part of the model. So how do we apply this? Well, the first thing is to take this in matrix form. So you have this representation, a vector of the three voltages at phase A, B, and C. On this side, equal to a resistance multiplied by the vector of current A, B, and C, plus the derivative of a vector of the flux linkages in phase A, B, and C. That is exactly the same than the equation in blue. For simplification, we present this in compact form, like this. This is the same vector, voltage A, B, and C, right here. Vector of current, vector of flux linkage. If we take this linear equation and multiply from the left by t, we obtain this. This is nothing else based on the definition we have. This one. You take a set of signals, ABC signals, you multiply from the left by t, and you convert them. So when we do that, here, this is nothing else than the voltage in DQ and zero sequence. Here, nothing else than the current in DQ and zero sequence. But here is a little bit tricky. T depends time, because this T depends on the angle theta. And the theta is changing in time because the rotor is changing. If the rotor rotates at synchronous speed, that theta will increase linearly. So this changing time, so we cannot put it inside the derivative. So we will leave it there. But this can be expressed by using the inverse. Lambda DQ0 is equal to T lambda ABC. So we isolate for lambda ABC, and we obtain this. So the mathematical difficult part here is to work with this and see what we obtain. I'm not going to ask you to do this multiplication. It can be tedious and it's not easy. But trust me here, if we do it, we're going to obtain this set of equations. Okay? What do you see here? Something beautiful. What is that? This part doesn't change. It's voltage at the terminal in DQ0 and current voltage drop in the resistance using the current DQ and 0. But here we have this set of equation for this part of our transformation. What do you see here? We discussed this in 325.
Is the effect of how a rotor's flux is linked with the flux in the stator.
Yeah.
That's just the description.
And we formally define this in 325 as a transforming voltage and a speed voltage. Because the reference frame is rotating at synchronous speed, hopefully, it will have some dynamic and change. We see here the speed voltage due to the rotation of the rotor. That's the speed voltage we have in DQ and 0 frame. But this is going to be the transforming voltage. But this is related to those quantities that in a steady state should be 0. This is the flux linkage in E axis and flux linkage in Q axis. These, as you can see, and this is the beautiful part, do not have any term that depend on time directly. We did have that with the signal for A, B, and C, voltage and current. And that can be tedious. Here, we got rid of the direct dependency of time. And this is a way much simpler to model and to analyze. So right here, if we replace this equation by this, that's basically the part transformation in the new model. Okay, but we are engineers. We don't want to do complicated things when they're not necessary. We want to solve complicated problems with simple tools and models. So these can be still simplified. So what is the simplification? If you look at this equation and the physical behavior of each of these equations, physical phenomena, we can observe that the dynamics related to this flux, dq0, these are the flux linkage, the transform flux linkage of the phases A, B, and C. These are the flux linkages of the stator. If you observe how these change in time, these are going to be very fast, very fast. If you compare with this, we might better represent this by algebraic equation, meaning they can change instantaneously. The energy involved in this flux, in the field related to this winding in the stator, is so tiny with respect to this that we better assume that that energy is zero and the variables can change instantaneously. And the same thing will happen with the 1D and 2Q dampers. So in this model that we have, that is accepted by industry and academia, then we can assume that all these equations that I have in blue are very fast, and we can assume that they can change instantaneously. And we will prefer, instead of having differential equation related to this, we prefer to describe them by algebraic equation. So the model now get transformed. We did that at the beginning of chapter 5. I make that, oh, I am way past time. Nobody said anything. Let me close this part. We, at the beginning of today's class, I describe this again. We're assuming that the dynamic of the grid are fast enough. We can neglect that energy stored in the grid and assume that the model we have is algebraic, and that was the representation. So similar thing we will do with the dynamics involved with these variables, and we will obtain a combined model. What this combined model will have: differential equation, state variables, and algebraic equation and algebraic variables. And that's going to be the standard model. How we will arrive to that in details, we cannot cover that in this course, but at least you have an idea. You have a motivation, where this thing comes from and why. Okay? So please go through the notes, go through the problems. Maybe you don't have time to work out the problems completely, but take a look and see if you can have an idea how to solve them. If you have questions, we can talk about that on Wednesday. Yeah. Any question? No? Thank you, guys.